The topic today is concavity and the second derivative test. This is coming from sections 5.1 and 5.2 in the textbook. The first example we're going to do is determine the points of inflection of the function f of x equals x to the fourth minus 4x cubed. Now, just making sure, you should have already looked at your note cards for today where we defined points of inflection, and that's going to be anywhere that the second derivative equals 0 or is undefined and changes from negative to positive or positive to negative. So it has to change signs in order to be considered a point of inflection. So, and points of inflection can be abbreviated POI for short. In order to find these, first step is find the first derivative. We need to find the first derivative before we can find the second. So that's going to be 4x cubed minus 12x squared. And now the second derivative is going to be equal to 12x squared minus 24x. So we're going to look at this. Can this function that we have for the second derivative ever be undefined? No, it's quadratic. It's defined for all values of x. Can it be equal to 0? Well, let's set it equal to 0 and find out. Is this factorable? Yes, it has a greatest common factor of 12x times x minus 2. And if you set each of those factors equal to 0, that means x equals 0. Or it's supposed to be a minus, x equals 2. So, if I draw a number line and put those points on it, x equals 0, x equals 2, I need to make sure that the sign of the second derivative has changed at each of those points in order to consider them a true point of inflection. So I need to choose a number. I need to choose numbers between and beyond those zeros of the second derivative to test and find out if it is indeed positive or negative. So these values could be anything, but we like to choose easy numbers to work with. Something easy, less than 0, would be -1. Something easy between 0 and 2 would be 1, and something easy greater than 2 would be 3. So I'm going to substitute those three values into the second derivative function. F double prime of -1 would equal 12 times -1 squared minus, oops, it's supposed to be squared, 24 times -1. Now, I really don't care what the value itself is of this. I'm really looking for a sign here, and this is definitely going to be positive. So I've got positive values for my second derivative when I'm at x values less than 0. Now f double prime of 1 is going to be 12 times 1 squared minus 24 times 1, which is a negative, so it did change signs at 0. And lastly, f double prime of 3 is 12 times 3 squared minus 24 times 3, and that's going to give us a positive. So it changed signs also at the 2. Now, I'm not quite done with this problem. I'm going to go and continue it on the next page. I know that I'm going to have my point of inflection at x equals 0 and at x equals 2. But by definition, a point of inflection needs to be a point, which means it should have both an x and a y coordinate. So, to find the y coordinates that correspond to these x values, I must substitute those x values into the original equation to get the y outputs that belong with them. Oops. So, if you'll remember, the original function was f of x equals x to the fourth minus 4x cubed. So f of 0 would be 0 to the fourth power minus 4 times 0 cubed, which equals 0. So the first point would have x of 0 and a y of 0 also. And then f of 2 is going to equal 2 to the fourth power minus 4 times 2 cubed, which is 16, minus 8 times 4 is 32. So that's going to give me negative 16. So my points of inflection are 0, 0, and 2, negative 16. That's the answer. Okay, our next example, number 2, is determine the open intervals on which the graph is concave up. Alright, we're given this function, f of x equals x over x minus 1. So, from your note cards that you got today, concave up means that the second derivative is positive. So I'm going to need to find the second derivative and find the x values where it is positive. So to find the second derivative first, I have to find the first derivative. Since this is a quotient, I'm going to have to use the quotient rule, which we learned earlier. Bottom times the derivative of the top minus top times derivative of the bottom, all divided by the bottom squared. Or you might have done low d high minus high d low, all over low low, whatever way you remembered it. So the bottom denominator there is x minus 1. The derivative of the top is 1 minus top is x times the derivative of the bottom, which is 1, all over the bottom squared. So this is equal to x minus 1 minus x over x minus 1 squared, which is just going to be negative 1. And I'm going to go ahead and write this as x minus 1 to the negative 2 power. Since I'm going to have to find the derivative of that, I can find the derivative of that to get my second derivative by using the chain rule. Derivative of the outside function is going to be negative 2 times negative 1, which is 2. Copy the inside, subtract 1 from the power, and multiply by the derivative of the inside function. So this would be 2 over x minus 1 cubed. So I'm going to set that equal to 0, and if I multiply by the denominator on both sides, or if I were to cross multiply, I'm going to get 0 equals 2, which is not a true statement. So this function is never equal to 0. However, if you'll remember, points of inflection can occur at places where either the second derivative is equal to 0, which this one never does, or at places where the second derivative is undefined. Now, where is this second derivative undefined? Where the denominator equals 0. What x value would cause the denominator to equal 0? 1. So, when x equals 1, f double prime of x is undefined. So that's going to be a potential candidate for a point of inflection. So 1. So I need to choose a number smaller than and greater than 1. So I'm going to choose 0 and 2. And I'm going to substitute those values into this second derivative equation to find out if my curve has a positive or negative second derivative, which would then tell me about the curvature. So here's my second derivative, 2 over x minus 1 cubed, and I'm going to sub in my 0, which, again, I don't really care about the number itself, but that is going to come out to a negative. And then I want the second derivative at 2. And that's going to come out to a positive. So, on my number line, 1 was the place where it was undefined. At 0, I'm negative, and at 2, I'm positive, which means that I am concave up, which is what they asked me to find, on the interval from starting at 1 going on toward infinity. And it wanted open intervals, so we don't include any of the endpoints here. That's the answer. Okay. Example 3. We're going to determine the x coordinates of the inflection points of f of x equals x to the 6th minus 5x to the 4th. So, I'm going to find my second derivative. First derivative is 6x to the 5th minus 20x cubed. Second derivative, 30x to the 4th minus 60x squared. Set that equal to 0. This is never going to be undefined. It's a polynomial. It's defined for all values of x, all real values of x. So the greatest common factor here is 30x squared, which would leave behind x squared minus 2. And now if I set those factors equal to 0, I get x squared equals 0, which means x equals 0. And I get x squared equals 2, which means x equals the positive or negative square root of 2. So, if I draw my number line here, I'm looking at 0, positive square root of 2, and negative square root of 2 as being potential inflection points. Now, it's not enough to say those for sure are. I have to test values between and beyond each of those to see if the sign changes. Okay? So, what is a number smaller than negative square root of 2? Hopefully you have a concept of negative square root of 2. We're going to say negative 2 is smaller. Negative 1 lies between negative square root of 2 and 0. 1 lies between 0 and the square root of 2. And 2 is a number greater than the square root of 2. So I'm going to sub in these 4 values into my second derivative equation here to find out if it is positive or negative. So f double prime of negative 2 is going to be 30 times negative 2 to the 4th power minus 60 times negative 2 squared. That's going to be 30 times 16 minus 60 times 4, and that is going to be a positive. So I have positive values here. Now I'm going to sub in negative 1. 30 times negative 1 to the 4th minus 60 times negative 1 squared. That's 30 minus 60, that's a negative. And now if I put in positive 1, 30 times 1 to the 4th minus 60 times 1 squared, 30 minus 60 is again negative. And last, f double prime of positive 2 is 30 times 2 to the 4th minus 60 times 2 squared. I'm running out of room. That is going to come out to a positive quantity, 30 times 16 minus 60 times 4. Positive quantity, yes. So positive here. So, points of inflection occur when the second derivative is either 0 or undefined. It's never undefined, but we have zeros at x equals 0 and at x equals positive or negative square root of 2, and where it changes signs. I change signs at negative square root of 2 from positive to negative. I do not change signs at 0. It's negative on both sides. But then I do change signs again at x equals the positive square root of 2. So there are 2 answers. X equals square root of 2 and x equals negative square root of 2. Alright. Example 4, which is our last example, says use the second derivative test. Oops, so hard to write with this stylus. And my handwriting looks like a kindergartner's. Use the second derivative test to find all the relative extrema for this function f of x equals negative x cubed plus 3x squared minus 2. Okay, so you should have a note card with the second derivative test on it. The second derivative test says that if the first derivative equals 0 and the second derivative is negative, you found a relative maximum. If the first derivative equals 0 and the second derivative is positive, you found a relative minimum. And if both equal 0, the test fails. So we're going to need the first derivative and find its zeros to begin with. So f prime of x will equal negative 3x squared plus 6x. That is never going to be undefined. If I set it equal to 0, there is a greatest common factor here, negative 3x times x minus 2, which gives me x equals 0 and x equals 2. So those are the places where the first derivative is equal to 0 are potential relative maximums or minimums. So I have a potential maximum or minimum when x is 0 and a potential maximum or minimum when x equals 2. So now I'm going to find my second derivative, which is negative 6x plus 6, and I'm going to sub in the 0 to start, which gives me a positive. Oops. Positive 6, but the number doesn't really matter. What matters is the sign. So if I am positive for my second derivative, that means I'm concave up. And if my first derivative is 0, that means my tangent line is horizontal. This is at a minimum. Okay. Now let's check for the other one when x is 2. Negative 6 times 2 plus 6 is equal to negative 12 plus 6. That's a negative 6. This is a negative quantity. So my second derivative is negative. That means I'm concave down. My first derivative is 0, horizontal tangent line. This means I'm at a maximum at that point. Okay, so now we just need to know if we actually want the extrema. These are points where we have a maximum or a minimum. So we're going to find the y-coordinates that correlate to these by subbing these numbers into the original equation. F of 0 equals negative 0 cubed plus 3 times 0 squared minus 2 is negative 2, and f of 2 is negative 2 cubed plus 3 times 2 squared minus 2, which gives me negative 8 plus 12 minus 2, that's 2. So I have a minimum at the point 0, negative 2, and I have a maximum at the point 2, 2. Those are my extrema for this function. Alright, your assignment today is in 3 parts. There are some problems from the book from section 5.1, some problems from the book from section 5.2, and finally there's a worksheet that has 7 questions all on the front of 1 page. So homework coming from a few different places today. Good luck working with concavity and points of inflection.